So let's take a look at solving logistic equations. Now there are several differential equations when it comes to logistics, but the one in my opinion that I think is the easiest one to memorize is dy over dt equals k times y times L minus y. So if we're talking about population growth, dy dt is going to stand for the rate of change of the population with respect to time. K is going to be the growth constant. Y is the given population size at a certain time t, and L is going to be the carrying capacity or the upper limit. Now if you were to integrate this by hand, now I'm not going to integrate in this video, but if you were to, you would then get the equation, the standard y equals equation of L over 1 plus CE, or C times E to the negative LKT. So once again, L is going to be that carrying capacity, the upper limit. And then we have our growth constant K, the variable T that we plug in for the input to get out a Y value or an output, and then C. And keep in mind that unlike exponential equations, in logistics, C is not going to be the initial value 99% of the time. The way you get your initial value in logistics is by plugging in 0 for T and solving for Y. Now it can be tough for some to memorize this y equals equation, so the way I memorize it is by just saying lice minus licht. So let's say for number 1 we have the differential equation dy dt equals 0.05y minus 0.005y squared. And we're trying to find the carrying capacity L and the growth constant K. So recall that the standard differential equation for logistics I mentioned earlier is dy dt equals k times y times L minus y. So notice this is not in the form of our standard equation, so we got to change that equation. So in order to change it, I'm going to start out by factoring out 0.0005y from the equation. So when I do so, I'll get dy dt equals 0.0005y times what's left in the inside. So when I factor out 0.0005 from 0.05, I'm basically dividing. So 0.05 divided by 0.0005 gives me 100 minus y. And so now it is in the same form as our equation, so we can just identify what our L and K values are. So the K value is 0.0005 and the L value, or the carrying capacity, is 100. So L equals 100 and K equals 0.0005. So now for number 2, let's say a certain national park is known to be capable of supporting no more than 100 bears. 10 bears are in the park at present, and the population growth of bears can be modeled by the logistic differential equation dp over dt equals 0.001p times 100 minus p. So for A, solve for p as a function of t. Now keep in mind that dp dt, dy dt, they're basically the same thing. P is usually used to represent population growth. So remember, dp over dt. So instead of dy dt, I'll write dp over dt this time. And that's going to equal to k times p times L minus p. And so notice this is in the form of our formula here, so we can identify our values. So if k is going to equal 0.001, or 1 over 1,000, and the carrying capacity L is going to be 100. So once again, solving for p as a function of t, we're just going to use our standard y equals equation, or in this case we'll put it as p equals. So p is going to be equal to L over 1 plus C times E to the negative L times K times T. So plugging in all our variables here, L is going to be equal to 100, so the carrying capacity is always on top, over 1 plus C, which we have not identified yet, but we'll figure out later, times E to the negative L times, and so L times K would give us the value of 0.1, so we'll have negative LK, so negative 0.1 times T. And so that is the logistic model of P in terms of T. But now we need to find what C equals. So notice it says 10 bears are in the park at the present moment, which means our initial value is 10. So at t equals 0, this tells us that at t equals 0, when time is 0, there are 10 bears in the park, so our population is 10. So we can just go ahead and plug those in and solve for C. So when I do so, we'll get 10 equals 100 over 1 plus c times e. Now, well, no matter what the t value is, or no matter what the k value is, or the L value, when I plug in t for 0, when I plug in 0 for t, that will make it 0. So we'll get e to the 0. E to the 0 is obviously 1, so we can just go ahead and erase that, because 1 times c is just c. So now in order to solve for this, I can just reverse these two and switch places. So we'll get 1 plus c equals 100 over 10, which is 10. And then so subtracting 1, we'll get c equals 9. So that is the c value that I'm going to plug in to the population growth equation, or the logistic equation. So we'll get p equals 100 over 1 plus 9, which is a c value, times e to the negative 0.1 t. And so that is the formula of p as a function of t. So now for letter B, we have to use our solution to A, which we just found, to find the number of bears in the park when t equals 3 years. So all we have to do is plug in 3 for t. So we'll get 100 over 1 plus 9e to the negative 0.1 times 3. And so when you use your calculator to plug in these numbers, you should get an answer of around 13 grizzly bears. So now for letter C, use your solution to find how many years it will take for the bear population to reach 50 bears. So notice it gives us a population, so we have to plug in 50 for our p value. So 50 is going to equal 100 over 1 plus 9e to the negative 0.1 t. And so you can either solve this by hand, or you can use a calculator and graph both of these functions and see their intersection point and define what x value or what t value they intersect at. And so solving it by hand, once again I'm going to switch both these places. So we'll get 1 plus 9 e to the negative 0.1 t equals 100 over 50, or 2. So then when I subtract over the 1, 9e to the negative 0.1 t equals 2 minus 1. And so e to the negative 0.1 t gives us 1 over 9. Now to get rid of the e, I can natural log both sides. So when I natural log, the natural log and the e's will cancel. So negative 0.1 t equals a natural log of 1 over 9. So then t is going to be equal to negative natural log of 1 over 9 over 0.1. Or dividing by 1 over 10, which means multiplying by 10. So we'll get negative 10 times the natural log of 1 over 9. And if you use your calculator, you should get the t value of around 22 years, which is the same thing as a negative 10 times the natural log of 1 over 9. So now let's say there's another question where it asks for when is the population growing the fastest. So always in a logistic equation, when it's asking for when the population is growing the fastest, all you have to do is take the carrying capacity and divide it by 2. And so if the carrying capacity is 100, we'll just take 100 over 2. And so we'll get at 50. So when the population is at 50 bears, that is when it is growing the fastest. And so if you want to find at what time specifically that is at, then we know right here that it's at around 22 years.